All right. Welcome back to. Welcome back. I don't know. I said welcome back. Welcome to page 2 of the notes. So, welcome back to the notes. And now you're on page 2. And we're going to do. We're going to talk about what the Jacobian is. And then its implementation when we're doing double integrals and also triple integrals as well. So the Jacobian of the transformation of t given by x equals g. So when we're, transforming our regions, we're going to put x in terms of uv and y in terms of uv. To do that, we're also going to have to take into account the Jacobian. So the Jacobian is the partial of xy over the partial of uv. And so basically what that means is we're taking every permutation that we can have with partial derivatives. So we're going to take the partial derivatives of x with respect to uv and the partial derivatives of y with respect to uv. And then we're going to find the determinant from these. And so that's what we're just working on. We're just finding the determinant, and that's what's going to give us the Jacobian. All right? So the Jacobian is basically the determinant of all the permutations of partial derivatives of our function. All right? And again, we're putting this in terms of x and y in terms of u and v. So that's why it's the partial of x with respect to uv and the partial of y with respect to uv. All right? You change the variables in a double integral. Suppose that T is a C1 transformation whose Jacobian is a non-zero and that maps a region S in the UV plane onto a region R in the XY plane. Suppose that F is continuous on R and that R and S are type 1 or type 2 plane regions. Suppose also that T is 1 to 1 except perhaps on the boundary of S. Then we can take the double integral, and when we do our UV substitution for our double integral, when we're changing the regions or when we're transforming the regions, all right, where it's basically going to be the same. It could be du or it could du dv or dv du depending upon how we're going to bound the integrals. So I mean that's not tied to what that has to be, but we're going to have to multiply by the Jacobian, right? The absolute value of all of the permutations of our partial derivatives or the determinant of the partial derivatives. All right, so that's what the Jacobian is. So, again, one thing that you do not want to forget is that dA is going to be the Jacobian. You don't want to forget the Jacobian. Again, it's just like when you have polar coordinates, and sometimes you might forget r, dr, d theta. That r was the Jacobian for polar coordinates. All right, and so now we're going to see, okay, this is where the r comes from. So we're going to show that the formula for integration in polar coordinates is a special case of Theorem 9. Special case meaning, when we're transferring from rectangular to polar, it's always going to be in this form. So if I'm going from rectangular to polar, the first thing that I'm going to do is go from x is equal to, or I'm going to change x. So I'm going to change x in terms of r and theta. And we know what x is in polar coordinates. X is just r. That's not an r. R cosine theta. And then y is equal to, we're changing the variables, I guess we can call that a different function, so we'll call it h. And that's going to be r sine theta. So in order to, write our double integral, so here we're going from a to b and theta to beta, same thing. I'm going to put my r on the inside because I know it's r dr d theta, so I'm going to put theta on the outside. Well, theta is between alpha and beta, so I'm going to put that on the outside, alpha and beta. And the inside integral is going to be defined, our r is going to go from a to b. All right, and then we're going to have our function. And so instead of saying f of xy, we're going to go ahead and say f of r cosine theta for x and r sine theta for y. And then we have our dA here. All right, well, again, our dA is defined by change this color so to distinguish. So dA is defined by the Jacobian, the partial of x, y over partial of v. And so in this case, r theta. And so again, that's going to be the partial of x. Hopefully I have enough room. Over the partial of r, partial of x over the partial theta, partial of y over the partial r, partial y over partial theta. So let's go ahead and do that. So when we take the derivative of x with respect to r, that's just going to be cosine theta. When we take the derivative of x with respect to theta, it's going to be negative r sine theta. Take the derivative of y with respect to r, so it's going to be cosine theta. No, I'm sorry, I was looking at, so it's going to be sine theta. And then take the derivative of theta with respect to, take the derivative of y with respect to theta, that's just going to be r cosine theta. All right, so the Jacobian, go ahead and multiply cosine times r cosine theta, so r cosine squared theta minus, but then you have a negative, so it's going to change it to plus r sine squared theta, r sine squared theta. And, well, if I break this up to r, pull out or factor out an r cosine squared theta plus sine squared theta, then that's just going to be 1, so it's just r, where r, of course, has to be greater than 0 because r is the radius. So, dA, and let me write this. So, dA, it's just, the Jacobian times r2, the change in r and the change in theta. So dr d theta. So if that's dA, then, our final step would just be, if that's r, then dA is not going to be dA necessarily, it's going to be the Jacobian r and then dr d theta. So here you see, that in polar coordinates, that's how we get r dr d theta. Again, you can also see it geometrically as we talked about finding, the area of that region, and we had that extra r there. But here you see it solved with the Jacobian.